The Polders package is a fantastic tool to handle any kind of data analysis. And in today's video, I want to show you 7 concepts out of Polders that help you do just that. Once you understand these 7 concepts, you can not only use Polders lightning fast speed, but you'll also be able to use its really smooth syntax to handle data analysis. So with that said, let's dive in. Alright, so in here in my script, I've already prepared a data set and loaded the packages that we're going to use in this video. What we're going to look at is the Palmer Penguins dataset, which is one of my most favorite data sets to practice data science on. You can see here in the console that it has a bunch of columns, namely 8, and it is just information about different penguin species living on different islands. And then there are a bunch of measurements about these penguins. Also, there's information on the sex, and also there is information on the year. The year here records when this penguin recording was actually taken. And here I don't want to work with all of the columns, which brings us to our first concept, namely how to select different columns from a data frame like the one we see here. You see, in a data analysis, you'll often want to only use a subset of the columns, and in Polders, all you have to do is to take the data frame and use its select method. In there, you can just specify the column names that you want to have. So for example, we could take the species here, or we could take a look at the bill length. Of course, we have to quote it. And then let's also use the bill depth. So once we execute only this part, we have only these 3 columns here. So this was really simple, but it is a thing that you'll do really often. Now let's do another simple thing where we, instead of take a subset of columns, let's take a subset of rows. So once again, we just take a method of a data frame and use it. In this case, it is the filter method. And what we have to do here is to stick an expression into this. And this already brings us to the next concept, which is expressions. You see, let's just go out of the filter function for a second and let's just talk about expressions here. What we can do is to use the column function from the Polders package to describe a particular column. For example, let's do bill length in millimeters. That is one of the columns we have already seen. And if we just take a look at this expression, we see in the output that it just outputs what we want to have here. And this fundamentally is an expression. It isn't necessarily tied to a data frame, but once I use this kind of thing inside of a method like select or filter, magic stuff can happen, and Polders will actually do some calculations. But at first, this column is really nothing but a specification of what we want to do. And for example, when filtering stuff, we might want to check, is a particular column maybe larger than some other value. We can do this in 2 ways. For example, we can just simply say, is that larger than 45? And if we execute this, we see that this returns yet another expression. The other way we could do this is to simply take one of these column expressions and then use one of its integrated methods to create these conditions that we're looking for. For example, here we were looking for greater than 45, and there is the GT as in greater than method, and there we could just stick in 45 here, and if we just execute this part here, you see that you get the exact same thing. If you want to have greater or equal, we could just check, let's see G, and then there is the GE function, or rather a method, and then if we use this, then we see here that we have greater or equal. So with these expressions, you can create filter conditions. And once you've understood this, you know how you can use the filter function. Namely, you could just stick in either this into the filter function, and you see that we have less rows now. For example, here, first we had 344 rows, and after filtering, we have only 166 rows. The same thing works, of course, with this part here. It's just a different way of writing it, but fundamentally the filter method just wants to have an expression. And the nice thing about this other syntax, though, is that if you use greater or equal than 45, then you could also use the not method on top of that to negate stuff. This is how you could chain together different conditions here. But for now, let's just go with this here. This is the data set we have, but possibly this is still too large for something we want to try out. So let's sample this down further. So we could think that this currently is the type of data we want to work with, but we want to see all of the results. So why not sample this to a specific, or rather a random set of rows. So here we could just take 10 rows, and you see here that my code was reformatted because I saved and I have the rough formatter installed here. For me, I like to add trailing commas here so that the rough formatter puts things on separate lines here. Same thing works in the filter function so that I can read this more easily following the steps. But that's totally optional, you don't have to do that. In any case, we can use the sample function here, and you see that now we're left with 10 rows and we see all of the rows that we have. But here, whenever I recall this function, I get a different set of rows, and the reason why is because this is random. And to make the randomness go away, we could specify a seed and then just take some number like 1, 2, 3, 4, and that way we will get always the same set of rows when sampling the data. So this is a little dummy data set that we can work with. Let's save this into df penguins selected. And let's just save it like this so that we can play around with this data set now. So we have learned about concepts like select, filter, and polars expressions using the PL call function. Let's move on to something where we actually calculate something new. For example, we often want to calculate new columns for our data frame. And this can be done using the with columns method. All you have to do is take a data set and then use the method with columns. And then you already see here in the documentation that it expects expressions. And we've already established that we can generate expressions using PL call and then doing stuff with it. So here we could try to divide these two columns by one another to calculate the ratio of the bill length to bill depth. So what we do is we take the column millimeters and we divide this by the other column bill depth by millimeter. And if we only execute this part here, once again, we see that it is just an expression. It turns into actual calculations within the with columns method. So as I execute this now, you see that nothing really happened. And that's because we haven't actually assigned it to a new column. So let's just call this column ratio. And now if we do, we see that we actually have a new column here. But still, it's odd that you'd think that something changed. And in fact, something did change. If you take a look at the bill length that we have here, it's 45 something something. And here the bill length is 2 point something, which is the ratio that we have. So what you can take away here is that if you don't specify an alias for where the new data is calculated in or where it is stored in, then polars will just take the first expression and override it. So this is why the bill length millimeters column here was just as in the original, but in our previous code where we didn't assign anything, just used the expressions, you see that the first column was overwritten. That's something to keep in mind here. But once you do that, you should be fine. But just to be sure that you understand what we mean here, let's just do another example. Let's just calculate another column. For example, we could specify that a penguin has really long bills if the bill length is larger than, I don't know, let's just do 50 here. So every penguin that has a longer bill than 50 millimeters should be classified as having long bills. Speaking about long bills, if you enjoyed this video, then I'd appreciate if you hit the like button to let me and the YouTube algorithm know that this is a cool video. And who knows, maybe at the end of the day, if a lot of people click on this video, it helps me to pay my long bills. I know, terrible pun, but I used it anyway to drive home the point that you should click the like button. So thank you for that. And now let's do some more calculations here. So here I said we wanted to classify the penguins. So let's do as long bill, or rather let's not save this into new column yet. Let's just use the PL when function here to make this if else kind of calculation that I've talked about here. So when the column bill length millimeters is larger than 50, this is how you do it in combination with this the when method from the polars package, then we want to have a literal true here, and otherwise we want to have a literal false here. So here Python is already complaining that positional arguments cannot follow keyword arguments. So we should technically assign this to a variable. And if we do, the complaining is gone and we can actually let our auto formatter format the code. And now we see here that we have a new column that we have named has long bill, and it is a couple of trues and falses. There are a couple of things to watch out here for, and this is why I've chosen this example. If you want to hard code values to be assigned into a specific cell of a table, then you use this literal here. And the reason why you do that is that if you use trues and falses here without the literal, then things still work out because it is a Boolean, but it is kind of dumb if this is actually not Booleans, but strings. For whatever reason, you might want to encode this as strings. And then if you execute this, you see that it cannot find the columns true because the polars expression now is looking for true and false here as column names, because with strings this happens. So this is why I've introduced this literal thing that you can use to save yourself from this mistake. If you use the literal function here and also use this over here, then things work as expected and you have a string column now. Also, one of the things I wanted to stress here is using this PL when, and if we move this up and redo this, then we see that, okay, this was now written into a column called literal, because apparently this PLit thing does this for us. I just wanted to stress here that there is another way of assigning names, and this is something you might encounter when you talk about polars. When you look into polars online, then you'd see sometimes people using alias. And there you could stick in a name, and then this name is used as a column name. So there are two ways of assigning column names, either by using this alias method at the end of your calculation or using this name at the beginning of your calculation, or rather in front of your calculation. Either way is fine. I just wanted to show you both ways here. So now that we have learned about new columns, let's talk about the next concept, namely summarizing a column to one specific value. And inside of polars, you can do this with the select method as well. So let's do select, and then we can not only select columns, but we can also summarize to a specific value. For example, we could say the mean is supposed to be calculated from the bill length in millimeters, and from there we apply one of the many methods that can be used on a column. There are a bunch of these kind of functions. In our case, we want to use the mean function. So if we do that, we see that everything was summarized inside of the bill length column to the mean value of this column. But watch what happens if we don't use a method like mean that summarizes a whole column to one value. For example, we could look at the ratio again and look at its rounded down value. So what we could do is we could take the column here, replace it by a ratio, and then use a different method, for example, the floor method that rounds values down. And now if we execute this, we see that we don't get a data frame with only one row, but multiple ones where this one mean value is duplicated, but the ratios here are actually the original ratios, but rounded down. We could compare this by also sticking in the ratio column using the PL function again. So we see here that the original values were rounded down. So that's something to keep in mind here. The select method allows you to not only select specific columns, but also to summarize them or mutate them if needed. Personally, I like to use all new calculation in with columns, but for the summaries, I'd like to use the select function. So one more thing that you might like to do is to summarize things by a different column or by a group. For example, inside of our data set, we have different species. So it might be useful to calculate the mean and the ratio bounded down list by species. And we can do that by just taking this stuff here, and then instead of using select, we can use the aggregation method. But in order for this to work, we have to group by stuff first. So here we can just say, okay, let's group by the species column and then aggregate using the same aggregation methods we have used before. So now if we execute this, the output is different. First, we have all of the groups in the first columns, and then we truly have one row per group. You can see here now that the ratios rounded down, they were collapsed or they were summarized into a list that now holds all of the rounded down values. So that's something that will come in handy in a lot of data analysis, so make sure to take note here. So what if you now wanted to do a sort of grouped column calculation? For example, if you wanted to use with columns but sort of in a grouped fashion, then there's also a way to do that, and this brings us to the next concept. To show you that, let me just grab this stuff here. Let's get rid of this part here. And actually, let's just start with the original data set. Let's just start with this here. And now what we could do is to add another column that has the mean of the bill length for every different species in a new column. And you'd think that, okay, let's just call it mean species bill length, this new column, that's the name it's supposed to have. And then you just take the bill length column and apply the mean function. But if you do this, it will of course calculate the mean based on all data, so it doesn't distinguish between different species, and then it will just repeat this value. But if we want to make it so that the mean is calculated for each subgroup that we define via the species, so for each different penguin species, and then use that value inside the corresponding rows depending on what species we have, then there is a way to do that, and that uses the over method. So if we use over and say over the species, basically iterate over the species here, or partition your data over the species, then you see now that we have different values inside of the new column here. And what you also see is that the values, say for Gen 2, is always the same. Here we have this value, and there in a different row where we have Gen 2 again, we have the exact same value. So that's a kind of grouped calculation here that we can also use column-wise. And what you can do with this sort of calculation, this is why I'm showing you here, is you might want to calculate another column that checks how much does something deviate from the mean. So let's calculate the deviation by using the original column, fill length in millimeters, and subtract from that the column that we've just calculated. Stick in the name in here, and then we have the deviation of that. Now, if you wanted to not get the deviation using signs here, so not caring about whether it's plus or minus, then you want to apply the absolute value method here. But if you look into the polars package, you don't see abs here. But what you can do, which is nice, is to use the corresponding expression that we have here, which is just another expression as we've learned, and then use a method of the resulting expression. And we see here that it has the absolute value method, and then we can just use this and we get exactly what we want. Next, let us talk about many summary calculations. Before, we have done it for one specific column, namely here we've calculated the mean of the bill length column, but maybe we want to repeat the exact same thing for different kind of columns. Before we start copying this thing over and over and replacing the columns, let's figure out a smarter way to do this. Before I do this, let me add a trailing comma here so that my formatter makes this more readable again. So what we could do here is to define a set of columns in a list. Let's just take this. And then what we can notice is that the PL_call function, it also allows you to use a list of things, and then it automatically incorporates them. It now looks a little bit different, and I'll show you in a second why this looks different, which brings us to the column selection things. But for now, let me just show you that we can use this thing here inside of the select function. So let's use our df selected penguins again. Let's use the select function, and then let's say that we want to calculate the maximum here. So if we take a look at this expression here, we see that it's the exact same thing, but the maximum method was applied to all of the things that are in there. So if we just take the correct data frame, we see here already my IDE complains. Let's just use the correct one. We see now that we have the correct maximum. But now we see that, okay, it is the original column names inside of this data frame here, which is probably not what I want. I want to have the name reflect the calculation that I just did. And for that, there is the name attribute that we can use to append suffixes. And for that, there is the suffix method. And there we can just say, okay, the new suffix is _max. And now we see that the column names were changed. And now we can do the exact same thing using a different method, maybe the minimum, the mean, and then we have calculated a whole bunch of summary statistics for a bunch of columns. We, of course, could make this columns list much longer to iterate over even more columns. But for now, let's just stick with these two. They show the principle just fine. So I told you that I will explain what this thing is all about, the cs.byName. And if we look into the top of my script here, we see that we have already imported cs, where cs corresponds to the selectors from polars. This is a neat way to select things based on different kind of specifications. For example, we could just say, okay, the expression where we hard-coded things using the specific column names, this could be replaced by a different selector. And under the hood, as we see here, this selector that we have used here is by name. That's one of the selectors, but there are way more. For example, you could use CS float to target all columns which are of type float. So if we look into the original data set, we see that these are float columns indicated by the F. So we could also just replace this stuff here using CS float and then applying the method again. And then there it is. Here's the exact same result. And if we look into CS, then we see that there are a whole bunch of other kind of things. We could look at alphanumeric stuff. We could look at things that are Boolean. We could look at things by the index of their column. So for example, we could look at the third column or reference things by names. There are a whole bunch of these kind of things like contains, for example, select all the columns that contain a specific thing. For example, we could use this to use all the columns that have underscore millimeters in their name. We look at the result of this. It matches this kind of thing. It automatically translates to the matches function, which uses regular expression inside, which is something you don't need to care about here. I just want to make the point here that we can replace these things here with kind of selectors here, and we will get the same results. So that's a really powerful technique. And if you have a whole bunch of columns, this is a really nice way to program to iterate over different kind of columns. But it is a bit of a shame that we have so many columns, which is kind of annoying in a lot of cases. I probably want to have one row per calculation that I did. And the way to do that is to just unpivot this thing to rearrange the data. And with that, we have a nicer overview over all the things that we've calculated. So now that we have done this for summaries, let's do one last thing before you can run off, do some other thing. Let's create multiple new columns for a data frame instead of just summarizing these to single values. And for that, we can just first create a columns vector. Let's just calculate it by using the data frame, then select things according to our current selector function we want to use. And then we can access the column names using the columns attribute. And that way, if we look into columns, we have a list of columns again. Here it is the exact same thing as I've hard coded here, but I'm just showing you this here to drive home the point that you can calculate these columns using code basically. And what you can also do with that is to create expressions based on that. We can basically iterate over this thing. For example, let's do a list comprehension and say for a column in the cols, let's calculate expressions. So let's just do col, say this is the column we iterate over. And that way we execute this. We have two expressions now. This gives us a mechanism to put in expressions in here that do more than just nothing, basically, just taking the data as is. We could use this for some calculation. For example, in statistics, what you often want to do is you want to center things by the mean. So you just take the column and calculate the mean from it. And then once you have the deviation from the mean, what you often want to do is to divide this by the standard deviation. What you can do then is to take this thing and divide it by the same column where you use this column to calculate the standard deviation. And now what we have in here, let's just check this out, is we have an expression that is even abbreviated here, but still this calculation works perfectly fine. And we've already learned that we can just stick things into parentheses and then access the methods from the corresponding result, which is just another column again. So we can use the name as we have done before, and then also make this into a suffix or like add a suffix. And then let's do underscore normalized. And now if we execute this, the result still looks the same because everything is abbreviated here. But let's just save this into a list. And what we can do now is take our data set, use with columns, and then stick in these expressions in here. And then we see that we get the new columns build length millimeter normalized and build depth millimeter normalized as well, which are just the original data, but we subtracted the mean from that and then divided this by the standard deviation. So that's a really powerful technique, and I really enjoy this so much about polars, that we can assemble expressions that way. And once you have understood this, you can do a whole lot of stuff and run a whole bunch of calculations really easily. I hope you enjoyed this video. Let me know in the comments if you did. Also feel free to drop all of the questions about polars that I have left unanswered. And now with all of that said, I say thank you for watching, and I will see you next time.